All right, chemistry time. Today we're talking about matter. This is very basic. Today we're talking about matter. In fact, I would say every lesson of all year we're going to be talking about matter. Today we're specifically talking about the nature of matter itself as a broad topic. I'd really love if this thing would change to the screen configuration I want. There we go. Okay. Good. Okay, what's it? Matter and is that all? Light. Oh, okay. We're getting closer, but that's not broad enough. That's too specific. Matter and. Okay, yeah. Some waves manifest in matter. So let's not use waves because there are material waves made of matter. But we definitely have matter in the universe. What else is there? Payne was the closest so far. Payne said light. Is that all that's in the universe, just matter and light? No. So what do you mean? He means, when he says light, he means something broader than light. What is it? Thank you. Bless you. Energy. Are there ghosts? Is there a God? It's not within science to say. And so there might be other stuff, but this is the stuff for which we have direct, empirical, physical evidence that this exists. That doesn't mean there isn't other stuff that is supernatural. Like all nature is here. This is literally everything in nature. I don't mean black dry erase marker and whiteboard. I mean these three things, or these two things, are everything that is in the universe. But that we have evidence for, that we have direct, physical, empirical evidence for. Could there be other stuff? Sure. But this is the stuff for which there is direct, empirical evidence. There might be other stuff, but it's not within the realm of science. Remember, not being within the realm of science does not mean it's bad or useless. It just means that it's not something we can directly observe, repeat, predict, and then continue to develop into theories. Doesn't mean it's worthless, but this is just all we can talk about using science as a principle. Okay? Are there all different kinds of energy? Yes. Sure, but that's not really the point of this class. The point of this class, as we know, chemistry is the study of matter and its changes. So what are some broad categories of matter we could get to? I can think of at least two different ways to configure this. What's one way we could categorize the kinds of matter? What's one way we could break all matter into special categories? Well, what's one way that we could categorize matter? Okay, so yeah, there's what by its properties. What broad categories of matter are there based on its properties, based on its physical properties, like Brett just said? Solid. So a solid is one category. What are the other ones probably? Liquid, gas, plasma. I'm just going to put other because there are other. But these are, and you know these. Do you remember this from physical science? You remember all these, well, other is kind of a pretty vague word, but you remember all of these from physical science, yeah? Is there such a thing as combinations of these? Like, can you have something that is both a liquid and a gas? Yeah, like a mist. Something that's a real thing. That's part of matter. Matter is all the stuff, the physical stuff in the universe. Thank you. Oh, thank you. Very good. Yeah. These are the phases of matter, but all physical matter is one or more of these. We could break that up. Thank you very much. Could we have a solid that is combined with a gas? Sure. Styrofoam is a good example of that. And the styrofoam is a solid thing, but a large part of its volume is made up by air and gas. Could we have a liquid that is with solid? Yeah, Jell-O would be an example of something that's kind of like a combination between a liquid and solid. So this is one way we can categorize matter. All matter is one or more of these. But that's not the only way we can do it. And the reason I'm going to erase this now is because this is true and your book does talk about this. But one, you should remember from physical science, so we're not going to go in a whole lot of depth. And two, it's not really the point of chemistry. There is talk of states of matter in chemistry, but that's not really what we're talking about for most of chemistry. The other way we can categorize matter is what we were talking about primarily. Do you have a question? What is it?
So when I got like exactly next to mystery, they scrape it off, but the glue is taking off the reflection part.
Oh, just leave the glue on. I don't mind the glue being there. It's all dried up, right?
The flimsy ones you want us to take off?
Yeah, the glue should just come right off. So. Okay, the other way we're going to separate all matter in the universe is into substances and mixtures. And are these other types of the categories I just said? No, these are a whole separate category. A thing can be a substance and a solid. A thing can be a substance and a liquid. A thing can be a mixture and a solid. They're whole different schemes to categorize. Just in the same way that we could break up the whole high school into boys and girls, but we could also break up the high school into 7th, 8th, 9th, 10th, 11th, and 12th graders. So someone could be both a boy and a 7th grader. So this is just a whole different schema of breaking up matter. What's the definition of a substance? Sometimes we call this a pure substance. P-U-R-E. What's the definition of a substance? No, I don't want to hear the book's definition. I want to hear your definition. What defines a substance? Not even close. Kind of close, I guess. Okay, so examples, we have elements that are pure substances. What else could be a pure substance? Compound. In fact, those are the only two ways that an element, or so that a substance, a pure substance can exist, is either as an element or a compound. How do we know if it's an element?
It's right there.
Yeah, so we can recognize it from the periodic table. But the definition of an element is that it only has one kind of atom, only has one arrangement of protons in a nucleus. That's the definition of an element. So in an element, it would be only one type of atom. Only atoms with 6 protons, right? That would be a pure sample of carbon. And a compound then will have 2 or more atoms, but in a fixed ratio. They have to be chemically combined and in a fixed ratio. And I'm going to put, instead of in, I'm going to put chemically combined. Chemically combined in a fixed ratio. This has got super messy. No one on watching the video is going to be able to read this, but I'm going to say it again. 2 or more atoms, chemically, but in a, I'm just going to rewrite the whole thing. This is a trash. 2 or more atoms, chemically combined in a fixed ratio. Give me an example of each. What's an example of an element? I'm going to move my mixture sign to somewhere else.
Helium.
I'm going to erase energy here. Energy does still exist.
Wait,
I'm just gonna move it over here.
actually, let's do hydrogen, so we can do oxygen and we make H2O.
Someone said helium, so we're going to have an example of an element is helium. There are obviously others. Anything on the periodic table is an element. What's an example of a compound? Lemonade is a compound?
H2O. It's a compound. H2O.
Lemonade is a compound? That was my question. Uh-oh, now we have some...
H2O and sugar.
You've just said something that makes me know that it's not a compound. It's a, you just said, it's a... Yeah, he just said it's a mix of H2O and something else. So that's definitely a mixture. So lemonade doesn't count.
H2O does.
Okay. Water is a compound. The thing that makes it a compound is the fixed ratio. We call the law of definite proportions. The law of definite proportions. I'm gonna, if I can find it in the book, I'm going to read you the law of definite proportions.
Can you think of any way that we could like heat up the glue a little to make it a little
You could use, there's a heat gun in the top, very, very, very back of the lab on the next shelf from the
like
top.
in that cabinet?
No, it's in the lab cupboard, like in the closet. The law of definite proportions states that a compound is always composed of the same elements in the same proportion by mass, no matter how large or how small the sample. So in H2O, it's always for every one oxygen part, it doesn't even matter. It doesn't even have to be for every one oxygen atom is true, but it could be for every one oxygen kilogram. There are 2 hydrogens. Whatever amount of oxygen we have twice that much hydrogen. What I just said was false. If we have 1 kilogram of oxygen, we won't have 2 kilograms of hydrogen. That's not the ratio of these 2 things. But they will have the set ratio by their mass. And the way we can find percent mass is this. Here's the math. Percent mass equals mass of element over mass of compound times 100%. This is in the same vein as if you get your percent on a test, you're focused on the score of the single thing, your test, divided by the total amount possible.
Mass what?
So the mass of the element, whatever the mass of oxygen we have, divided by the total mass of the compound will give us the percent mass. We multiply by 100% to give us 100%. So this fraction will, the solution to that will be a decimal, and that decimal times 100% will give us the percent mass of that substance in the compound.
So you basically multiply it. Never mind, I'm not even. Makes sense.
And then we also have this, and it's related, but the law of multiple proportions. Law of multiple. And this is almost like a corollary to the law of definite proportions. But the law of multiple proportions says that if we have a certain amount of x in xy is always the same relative to y. So the ratio of the elements are the same, is the law of multiple proportions. And those 2 things, really, they're corollaries of each other more than they are whole separate laws. So now we have this idea of substances, which I would say the simpler is the element. The simpler to understand is what I meant, but also obviously the simpler physically because it's just one kind of atom. And then there's also compounds, which have to have a set ratio, and they have to be chemically bonded. It is not a mixture. It is not a mixture. Water is not a mixture of hydrogen and oxygen. A mixture of hydrogen and oxygen is a gas. If we had a balloon full of just hydrogen and oxygen together, and they're just floating around, it's just a mixture. We saw that in the periodic table of videos. They had this balloon that had hydrogen in it, and there was oxygen in the atmosphere around it. And how did those combine? How did they cause them to chemically combine? Do you remember? What did they have to do to make the hydrogen balloon combine with the oxygen just floating around in the air? Yeah, they added, in their case, they added an electric match, which is just a little open circuit that will allow electricity to cross the gap, and it generates enough electricity there at that site that the balloon pops, but it also gives enough energy to this hydrogen that it can start bonding with the oxygen that's all around it. And it creates water. So once we have lit the electric match, we get H2O. And that ratio, and what was this like? What was this like? What were the properties of this? No, what were the properties of this? It's a gas. Pale blue gas. What were the properties of this? It's a gas. It's a lighter than air gas. And when we combined them, they made a liquid. Liquid water. With the properties we did. Why didn't we, do you think?
Because it evaporated.
Yeah, it was already evaporated. So we made water vapor. But does that water vapor have the same properties as oxygen and hydrogen?
Yes.
Try again. No, absolutely not. Yes. This has completely, please write this down. This is one of the most fundamental principles of chemistry. Completely, the compound has completely separate properties from its constituent. What's that word mean? Elements. What's constituent mean?
No idea.
Well, you better figure it out. What's constituent mean?
Spell it, please.
Yes.
Gas.
What's constituent mean? Completely separate properties from its constituent elements. Yes. The elements that make it up, that it's made out of. Completely separate properties from the elements it's made out of. So this is made out of hydrogen and oxygen, but it has completely separate properties from both hydrogen and oxygen.
Like you taught us that.
Yep, all of this is 100% review from physical science. Speaking of review from physical science, we have heterogeneous and homogeneous mixtures, which you need to know about and be able to provide examples of. You should know that mixtures do not have a set ratio, and that's the main way that we can tell them from compounds, is they don't have a set ratio. Speaking of our lemonade example, we can imagine a kind of lemonade that is 90% water and then 10% lemon juice and sugar, and we can imagine a kind of lemonade that's 10% water and 90% lemonade and sugar. Those are both lemonade. Well, one might not taste as well, it tastes bad, but they are both lemonade. But the ratio doesn't matter. These mixtures have non-representative, they don't follow the law of definite and multiple proportions. They can have any ratio of their constituent, in this case, compounds. But everything can be broken down into its elements. And in fact, mixtures can be separated. Either kind of mixture can be separated through various means. I'm just going to list the types of chemical separation, and then we will talk about them, or you should have learned about them through your reading and through your review. But we have filtration, distillation, and crystallization. Filtration, distillation, crystallization, sublimation, and chromatography. I'm not going to count sublimation, but chromatography. Filtration, these are all in your book, and they're all vocab words, and you should know, because you did your vocab, what's filtration?
Filtering something out.
Yeah, well, we have a mixture, usually, of a liquid with solid suspended in it. A mixture of a liquid and a solid. And we filter, and the liquid is able to go through the filter, and the solid is not able to go through, so it stays in the filter. In distillation, we're separating them by what physical property?
Distilling them?
That's not a physical property. No?
Boiling them?
Yeah, we're separating them by their boiling points. So we boil one, we have a mixture of liquids, usually. It's usually a mixture of liquids, but we have a mixture of two liquids, and they have different boiling points. So we get them warmer than the boiling point of one, but not as warm as the other one. And so the one that was surpassed its boiling point now boils and becomes a gas and is removed, and the one that's left over has the higher boiling point.
Mixture with, like, so you say you have river water, right? And you want to drink it, you have to boil it first. That's why, because you're distilling it.
No, the reason you would distill river water is so that the reason you boil river water is so you could kill all the germs because they can't survive boiling. Crystallization is where if we have a solution, which a solution is a kind of mixture. We usually just call a homogeneous mixture a solution. There are other kinds of homogeneous mixtures, but solutions are all homogeneous mixtures. But what it would be is a substance that is dissolved in a liquid, usually a solid, dissolved in a liquid. Dissolved meaning that now you don't even see the thing. It's not visible. We can't filter it because it has been dispersed chemically throughout. Something like salt dissolved in water. But we could crystallize it by letting the water evaporate, and what would be left behind is salt crystals. That's crystallization. And then in chromatography, we're able to separate the different components of a liquid based on how readily they wick through a capillary action. So what we would do in chromatography, and we might do this lab, but we usually will do this lab, but we have a wick of some kind. And we have a mixture of liquids, usually ink, and as a solute spreads across the wick, the more soluble particles that were in the solution will travel further along the wick, and then by the time all the solution or the solute has evaporated, the solvent has evaporated, what's left behind are different layers. I'm doing it in little circles because usually we do it on circular filter paper, but rings of the most soluble in that solvent down to the least soluble will be on the inside. And there's a picture you could see. I'll show you here real quick, but there's a picture. There's not a picture, but I wish there was. Your book also goes into the difference between physical and chemical properties and physical and chemical changes. And you remember those from physical science and their vocab words. And the one thing that's new, and these are just vocab words too, is extensive and intensive properties. The extensive properties are those that do not rely on how much there is. Sorry, that's the other way around. The intensive properties are the ones that do not rely on how much there is. They're the same for any amount of that substance, and the extensive properties do rely on how much there is. The change depending on the amount of substance. For instance, mass would be an extensive property, color would be an intensive property, usually. I'm trying to, oh, and then you should have somewhere, and I'm sure you have this from physical science, if anyone was even paying a modicum of attention, you should have the law of conservation
Nothing shall be created nor destroyed.
of mass, and you should have that in your memory and in your notes from physical science.
Question.
Yep, go ahead. Does anyone else have questions that apply to the lesson? I do like, there's this neat little table of types of solutions here on that. Focus. Well, the camera's not going to focus on those, but it's a neat little table of the, and this is on page 81 in my book, of solutions of, for instance, a gas dissolved in a gas, there's a solid dissolved in a liquid, and that's a neat table. Remember, all of those are homogeneous solutions, or homogeneous mixtures are solutions. Does anyone have questions over any of this?